So it says here in the previous investigation, we established the meaning of exponential growth and the growth factor. I kind of want to talk about that just a little bit before we kind of jump into this. Okay, so let's think about for a moment. If you have a function, say that it looks like that, okay? So the a can be any real number. The b is our base of our exponential function. Our base has to be a positive number for it to be considered an exponential growth or decay. If the b is greater than 1, it is going to be a growth. Now remember that 25% addition, that tax of 7%, anything that's added on to that 100%. So if our decimal is something like, let's say we had an 8% tax, so our decimal would be 1.08. That would be your base. If your base is between 0 and 1, but not equal to either of those things, then it's going to be a decay. Now we found that when there was like a discount, a 70% discount, or a 30% discount it was, that comes off of 100% and makes it that decimal between 0 and 1. And so that value would keep going downhill. The graphs of these ones, it's going to go uphill. The graphs of these ones, it's going to go downhill. So that's just a little bit about what those functions look like. We can transform them a little bit if our a could be a stretching factor if there's a number out in front. For most of these, it's just a plain old b to the x. Okay, so let's take a look at this example. It says, how large do numbers become if you repeatedly double them? Imagine you have a chessboard. Now, a chessboard is 8 by 8, so there's 64 squares. And you place 2 pennies on the first square, so there's 2 right here. Okay. And then you place 4 pennies on the second square, and then you place 8 pennies, and then 16 pennies, and you keep on that pattern. If there are 64 squares on the chessboard, without doing any calculations, make 2 predictions about how many pennies do you think will be on the last square. So give me some numbers. How many pennies do you think will be on square 64, whichever corner they decide is square 64? Give me a guess. You know, so you said 10 million. Okay. I think that's a reasonable guess. Okay, so let's just stick with that. Okay. And then it says, will it match something like the number of students at your school? Definitely not. I think it's definitely more than that. Because, I mean, we already have 16, 32, 64, 128, 256. Just by the time we hit the first row, we have 256. So it's definitely a lot more. I'd say probably by somewhere in this row, we would surpass the number of students in this school. The population of Los Angeles, I have no idea. Can somebody Google that for me? Tell me, what is the population of Los Angeles? She's on it. Isn't that silly?
3.822 million.
Okay, what is the population of the United States? Isn't it something like 34 million?
The United States is like 300 some million.
300. 333.3? Yeah. So we still are guessing that it's more than those, okay? So how tall would the stack of pennies be? Now let's just for a moment, let's think if the stack of pennies was 10 million high. Let's just go back to that number for a minute. A penny, we're gonna do some math here. Okay, so the thickness of a penny, or 598,425 inches, give or take. And then if we divide that by 12, and then divide that by, that's feet, then 5,280, it would be roughly about 9.4 miles high. If it is 10 million, okay, it would be 9.4 miles high would be our stack of pennies. So definitely taller than a house or a skyscraper. It would not reach the moon, but it definitely would be up there. Okay, I don't know what the layers of, when do you get to this layer above Earth or whatever. Okay, so let's we have a table here. Square number 1, we had 2 pennies, and then 4, and then 8, and then 16, and then the 10th one. What we can do is we are actually doing to whatever the square number is that we're on. So 2 to the 10th, on the 10th square, we have 1,024. And on the 30th square, oh goodness gracious, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have we have 1 trillion pennies on the 30th square. So I didn't think your guesstimate would be that bad, but that's ridiculous. Oh my gosh, look. Wait, my comma's there in the wrong spot. It's over 1 trillion pennies on the 30th square. So maybe it will reach some of the things that we thought of. Let's draw the graph, okay? So let's count by ones here. So that would be the square. And this would be the number of pennies. And let's go ahead and count. Let's go by tens. Okay. If we have, okay, on the first square we're at 2. On the second square we're at 4. On the third square we're at 8. On the fourth square we're at 16. On the fifth square we would be at 32. On the sixth square we would be at 64. So we can see that we can't have half a pennies or anything. So technically connecting them isn't really what would happen. But if we were thinking of the shape, if we could have a half a penny and stuff, that's what that would look like. Okay. So it says, how does the number of pennies in the chessboard vary as you move along the board? For example, each time the square position increases by 1, what happens to the pennies? Well, if you'll notice, for every 1 that we add on to our x, our value gets doubled. So if we increase by 2, it's going to be times 4. And if we increase by 3, it's going to be times 8. So what percent change? Now let's talk about what that means. If you increase the position by 1, so let's just go from here. Let's go from 1 to 2 as an example, okay? So the change, we went from 4 to 2. So let's call that f of 1 was 4. Or I'm sorry, f of 2 was 4, and f of 1 is 2. We went we want to change a multiple of 2. Now let's think of percent change, what that means. That is the same as 200%. So it went up by a multiple of 2, or 200%. Any of these, if we think about like here, 200% of 8 is doubling 8. That's adding, well, actually, let's talk about the change, okay? The change in percent. So the change, let's talk about that. So we went up by 200%, or we multiplied by 200%. I'm trying to think of a great way to explain it. So we were at 100%. We went up to 200%. So 200 minus 100 is 100% change. Because when we double something, we had 100%. We added on another 100%, if that makes sense. The change, it went up by 100%. So 100% of 8 is 8. We went up by 8. So 100% plus 100% is what gets us the 200%. I think that's a good way to put it, hopefully. Okay. So here we have the exponential function. Some people call the doubling function. You can see that it's continuously doubling. So we've got our function here. It says determine the value of f of 0. Well, if our function is 2 to the x, that's just 2 to the 0 power. Remember, anything to the 0 power is 1. So this is the point 0, 1. So a simple exponential function will hit that point 0, 1. Okay. It says when x increases by 1, the new output is 200% of the previous output. What is the percent change? Well, it started at 100%. It ended at 200%. Remember, it's always end minus beginning. And so it went up. It increased by 100%. As x increases away from 0, how do the function values change? So they get large very fast. I don't know what else they want us. So they get large quickly, I guess would be a good way to say it. As x decreases away from 0, how does the function values change? They stay close to 0. So we're talking about this end of the graph. It never hits it, but they stay close and get closer to 0. Now, why is that? Well, if we take a number like 1/2 and we square it, okay, so let's go. If we take 2 to the 1/2 power, I'm sorry, to the negative 1/2 power, a negative exponent flips it. So that would become 1 over 2 to the half, or 1 over the square root of 2. So if you take 1 over the square root of 2, I believe it's something like 0.7-ish. Let me tell you. Yeah, it's roughly 0.707. So that was at negative 1/2. At negative 1, it's going to become 0.5, and then at this one it might become 0.3. So it's getting ever so closer and staying close to 0 on this end. There is what's called an asymptote here. And as long as nothing is added on to that function, it will always stay at 0. So that's a little bit what the graph looks like. Now, if we could look at this right here. See that right there? Okay. It says we're going to add these functions to the graph, and I will be your partner. We'll do it together. So g of x is 3 to a power of x. And h of x has that 6 in front, so it's a little funky. But let's go back up to our graph. And let's add these functions to the graph, okay? So I'm going to make a table for each of them. So let's plug in -1, 0, 1, 2. Should be enough to get us there, okay? 3 to the -1 power is 1/3. 3 to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. I think that should give us a good indication of what's happening. So you'll notice again, like I said, it does hit that 0, 1 power, or 0, 1 spot, I'm sorry. At -1, we were up at 1/3. So roughly here we would have been up at 1/2. So 1/3 is, I mean, just a smidge over. 1 is at 3, just a little bit more. And then 2 is at 9. But we don't see much of a difference down at the left tail. But you notice what happens? When that base increased from 2 to 3, it is tripling things. And so we should expect that it's higher. That rate of change is quicker. Now, let's think about the 2/3 for just a moment. Okay, so now I'm going to make a graph with that 6 times 2/3 to the x. I'm trying to think of some good good ones to put in. Well, we can definitely do -1, 0, and 1. That'll get us at least close. Okay, so anything to the 0 power is 1, but there's a 6 there. So that one's 6. So let's do the easy one first. Okay, let's talk about -1. -1 on the 2/3 is going to flip it over. It's going to become 3/2. 6 times 3/2 is what we're searching for. 6 divided by 2 is 3. 3 times 3 is 9. So this one's 9. If we plug in 1, we get 6 times 2/3. 3 goes into 6. 2 times 2 times 2 is 4. So we have a 4. Okay. So I'm going to make this one in a different color so we can kind of maybe it'll pop out at us. Okay. So at -1, we were at 9. At 0, we were at 6. At 1, we are at 4. So we're just going to kind of guesstimate. Our graph. Well, let's plug in. Will -2 work out nice? -2 might work okay. Okay, let's do that. 6 times 2/3 to a power of -2. So it's 13.5. Yeah. So at -2 we're at 13.5. Okay. So our graph for this one looks, if I could draw, our graph looks something like this. Okay. Now, let's talk about what each piece of that graph did, okay? So for this graph, the 2/3 is a number between 0 and 1. It's a proper fraction. That's why our graph ended up going downhill. It is actually a decay function. So that's an exponential decay. All the 6 does is lift it up a little more. So if it was just the 2/3, it might be lower. What the 6 does is it kind of levels it off a little more. Okay. So at least you've seen what those graphs look like and how you would graph them. Okay. Just plug in the points. Now let's take a look at the, where it says here, the growth factor. So I would maybe, if you have a highlighter, if you're doing it on your iPad, here's the main thing to think about. When x increases from x1 to x2, so any 2 consecutive x's, f of x1 over f of x2 over f of x1 is called the growth factor. If you go 1 unit wide, then it is a 1 unit growth factor. If it's 2 units wide, it's a 2 unit growth factor. So you're just dividing the end divided by the beginning, okay? A growth factor is a useful number because it tells us how many times as large f of x2 is compared to f of x1. Note that if the factor is between 0 and 1, that is often called the decay. Remember I told you if our function looked like this, if b is bigger than 1, it's considered a growth. If b is between 0 and 1, it's considered a decay. So that's kind of what they're getting at as far as that little section right there. Okay. So now let's look at one more from our investigation. I just kind of want to do some about this problem right here. So if you want to look at problem number 4, it says from 2020 to 2025, home prices in the United States are projected to increase dramatically. From 2020 to 2025, the value of the specific home will increase by 16% per year. Without performing any calculations, predict the home value after 5 years. If its value increases 16% per year, will the value be 50%? Will the value double? What do you guys think? Do you think it'll be 50% larger than what it was? Do you think it will double? Would anybody have any ideas? What do you think? Do we have a prediction? Well, let's just, for the sake of argument, let's say that we think it might double. Okay. So what's happening is year 1, it goes up by 1.16. That's year 1. So it would be the price times 1.16. Year 2, you would multiply it again. Year 3, you would multiply it again. So on year n, we would take that 1.16 to the nth power. So what happens? Well, if you look in the chart for our first year, it went up by 16%. So multiply that by 1.16. So 280,000 times 1.16. This first time is 324,800. But it goes up again. So if we do it again, multiply by 1.16, now it's 376,768. Do it again. It's 437,000. I'm going to go to the nearest dollar. 51. Do it again. It's 506,979. Do it again. It's 588,096. Okay. So did it double? Well, 280,000 times 2 is 560,000. So it more than doubled in 5 years. Not much more. It's pretty close to doubling it. So let's actually draw the graph. We should expect to see that kind of curvature that we see before. Let's make these the price in thousands. And this will be the years. Okay. So we'll just count here by ones. Now we have to be between 300 or 280 and 580. So if we make this 100, 200, 300, 400, 500, and 600, it fits pretty well, I believe. Okay. So at year 0, time 0, whatever you want to call it, we're at 280. Okay. So that would be close to that 300 mark. At time year 1, we're at 324. So we have gone up a little bit. Here's the 350 mark. So 324, I'd say, is roughly here. Year 2, we're at 376, which would be roughly here. Just guesstimate. Year 3, we're jumped all the way up to 437. So that would be about there. Year 4, we jumped to just over 500. And then year 5, we jumped closer to, but not quite 600. So you can see that curvature. You can see that exponential growth because the home prices were going upward. So it's that has that curvature. If we could go backwards in time, which we can't, that graph would scooch that way. This end is getting higher and higher and higher. So we can multiply by 1.16 again and again and again each year. So the value of the home at one moment in time is 116% of the value from a year before. So the home's value at the beginning of 2025 is how many times as large as the beginning of 2020? So we're going to take the 2025 and divide it by the 2020. So we can see how many times it was. So 588,096 divided by 280 it became about 2.1 times more. So, and then it says, what does your model predict the home's value will be at the beginning of 2050? So remember, the year was 2020. 2050, we would have to, string our number out way past to get to 2050, and the value of the home would be very, 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 very large. Okay. So now could you please jump down to problems 8 and 9? Okay. So it says for these problems in A, we're going to find the ratio of output values that correspond to an increase of 1 in the input. So we're looking for that growth or decay factor. Okay. So let's do that for 8A. Okay. So we're going to take our f of 1 divided by f of 0. So it would be 4 divided by 16, or 1/4. That's also equivalent to 0.25. We could see that it's a decay. Do you see how these numbers are getting smaller and smaller and smaller? And each time they're dividing by 4. So that's why we get that to be that. So let's do how much did it change divided by the original, and then we'll make it a percent. Okay. So 16 was our ending, or 16 was our beginning, 4 was our ending. 4 minus 16 is negative 12. If we divide that by 16, 12 divided by 16, it went down by 12. That's what I was thinking it was. Okay. So it is a negative 75% change. Okay, so let me go over what you do again. We're trying to look at how much did it change and what percent of the original was it. So it's always ending minus beginning divided by the original value. So that would be negative 12 over 16. Get that decimal, then divide or multiply by 100, move it over 2 places to the right to make it a percent. Okay, there we go. C, identify or determine the value of the function when x equals 0. So we already have that. They did that for us. F of 0 is 16. Use the information from part A through C to define the function's formula. So our function's formula is, I'm going to show you how to do that. our original value has to show up first. So that is our A. So let me show you that. Remember I wrote this down for you earlier? Okay. So this is your A value. So whatever f of 0 is always your A value. So in this case, that's the 16. This number right here is going to be our B value. So f of 1 divided by f of 0 is always our B value. And so in this case, it's 1/4, and then it's to a power of x. Now, how can we check that we're right? If you plug in 0, you better get 16. If you plug 0 into that, you get 16 times 1. Yay, 16. Yay. But plug in at least one more. If you plug in 1, we get 16 times 1/4 to the first power, which is 4. The second one works. If I plug in 2, I get 16 times 1/16, which is 1. So this pairing 2, 1 works. So the best way to test your formula is, did it work? Okay. So let's do one that's a growth. Okay, so let's do the exact same thing for 9, please. Okay, let's do 9a. But that's going to be our B. Okay, so that's going to be 299 divided by 260. 299 divided by 260 is 1.15. That's our B. Okay. The change, our ending value was 299. Our beginning value was 260 divided by that original 260. So 299 minus 260. It increased by 39. 39 divided by 260 is a 0.15 increase, or a 15% change. So see how this number here was, you could also compare it with 1 minus 1.15. Same thing here, you could take that away from 1. 1 minus 0.75 or 0.25 should be a 0.75 change. Okay. We know that we got to find f of 0 this time. So each time it goes up by 1.15 or by 15%. So f of 0, we need to go down by 15%. So I think if we take our 260 number and divide it by that B we found in A, we should go backwards one step. So 260 divided by 115 is 226. We'll just call it that nice number. Okay. Remember, that is your A value. So once we find our A value and our B value, we are ready to make our formula. Okay. So f of x is our A value, 226, our starting value at the 0 mark, times our 1.15 to a power of x. So how could we check? So if you plug in 1, 226 times 1.15 does give you the 260 that's on our chart. 226 times 1.15 to the second power should give you the next number on our chart, and it does. And you could go down the line, and then you could check the numbers on the chart, and that could give you that. Okay. So that's a little bit about that. So go ahead and turn this in, and then please, 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 please go into your pre-class M43 for me. And we're going to do that, and then we're going to also talk about the homework a little bit. Okay, so this is talking about the pennies on the chessboard we just got done talking about. So our guess in class, did we say 10 million? Wasn't that our original guess? Okay, so let's put 10 million. Okay, and then let's fill in the pattern. 2 to the 9th. This would be 2 to the 19th and 2 to the 29th. They didn't want an actual number value, I don't believe. So just make sure Mine are 9, 19, and 29. Make sure yours reflects whatever your numbers happen to be. I don't know what yours are compared to mine. And then it says, go back and look at your prediction from the previous equation, then choose the best answer. If you hit the preview button, like on this one alone, my 2 to the 29th, we said 10 million. It's already 536 million in that spot. So I believe my prediction was too small. And I would assume that should be the same for you. And then I don't know if yours are the same as mine. I think they're shuffled a little bit, but okay. So I had to Google these things. The distance to the moon and back in inches, and I rounded roughly so that we could have a comparison purposes, is 3 times 10 to the 10th pennies to get, or I'm sorry, 3 times 10 to the 10th power inches to get to the moon. The area of the US in square feet, I use the same 10 to the 10th power. That's one of those. This is 10 to the 11th, which would make that 10 times 10 to the 10th. So far on the list, the Milky Way, the number of stars in the Milky Way is the biggest. The number of people that have ever lived on Earth, I had to Google that. That's bigger than the number of stars in the Milky Way, which I found wonderful. That's 10.8 times 10 to the 10th. But if you look at the number of pennies, we would have 2 to the 63rd, maybe 64th power. I thought they put 1 on the first, but they put 2 on the second. So anyway, even not quite the 63rd square is 10 to the 15th power. That's 5 more zeros than the number of people that lived on Earth. So this would be the largest, the chessboard. And then if we go down here, it says we're doubling a donation for $35 every day. So it started off at 35 at day 0, then it went to 70, then it went to 140, then 280, then 560. Write a function f that models the value in dollars and number of days. So f of n, the starting value always comes first. So that's our f of 0 number, which was 35. And then our factor of doubling to the power of n. They used n, not x. Okay. So that, for me, would be the equation or function they want on that line. So modify your answer to part B if Bob initially donated 85. Remember, the starting value is the number that should be sitting in front. So in my case, my 35 becomes 85. Okay, so that's that. So now if you could open up your homework 4.3, let's talk about that. Okay, so it says that we have this function, 3 to the x is an exponential function and is often referred to as the tripling function. For any value of x, if f of x plus 1 is how many times large as f of x? Well, let's think about for a minute that the next one would add x plus 1 in that power. And if you add exponents, the rule is if the bases are like and you're multiplying, you add the exponents. So we've added a power of 3. So for me, this would be 3 times larger. Now, for yours, it might be something that is more than that. If it's a 2, it's 2 times larger. If it's a 4 to x, it's 4 times larger, whatever. For any value x plus 2, now think about the first one we would have multiplied by 3, then we'd multiply it by again, so 3 times 3 is 9. If x increases by 5, that would be 3 to the 5th power. Now, I don't know off the top of my head what 3 to the 5th is, so I'm going to let 243. So I'm going to let iMath calculate that for me. Let's hope Mrs. Hott is correct. And so there you go. That's what they're meaning there. Okay. Let's take a look at the second one. It says in a function 3 to the x is often called the tripling function. Is yours the tripling function? Okay. So it says here that this is not the only example of a tripling function. Give two more distinct examples of tripling functions, functions whose values triple whenever the independent variable changes by 1. Well, you know, this one here implies that our starting value was 1, but what if we put a 2 in there? That means our starting value started at 2. What if we put a 4 in there? You can put whatever number you want, as long as your 3 that contains your x power is there. You'll notice that all of those will triple still. If I plug in 1 to our second one, it will triple it. From 2, it will go to 6, and then it'll triple it again, and then it'll, you know, go to 18 and so on. So any of those should be correct. So for the rest of class, we don't have a ton of time, but keep working on 4-3 homework because you have a lot of homework due this week. Remember, please, that all late work is due by Sunday. You're going to have 5 homeworks due Sunday. So this is a big, big week of lots of things to do. So please, please, please be working on iMath every single night.